How long is the coastline of Great Britain? It seems like a simple question with a single answer, but it isn't. The answer fundamentally depends on the length of your ruler. If you measure with a 100-kilometer ruler, you get one number. But if you use a 1-kilometer ruler, you can now measure the curves of smaller bays and inlets your larger ruler skipped over. The coastline gets longer. Use a 1-meter stick and it gets longer still, accounting for the perimeter of individual rocks. What happens if you use a ruler the size of an atom? The measured length approaches infinity, all contained within the finite space surrounding an island. This isn't a trick, it's a fundamental property of our world. This effect is described by fractal geometry. A fractal is a shape that exhibits self-similarity. It looks the same at any scale you view it. Consider the coach snowflake. You start with a triangle, then add smaller triangles to the middle of each side, and repeat this process forever. With every step, the perimeter of the snowflake increases, approaching an infinite length. Yet the entire shape never grows beyond a finite, easily drawn circle. The boundary line is infinitely long, but the area it contains is finite. This is a geometric line that has, in a sense, folded itself into a space far smaller than its length would suggest.
This idea of self-reference isn't confined to shapes. It can break logic itself. Consider the paradox described by Bertrand Russell. Imagine a set of all sets that do not contain themselves. Now ask yourself, does this special set contain itself? If it does, then by its own definition, it shouldn't. But if it doesn't contain itself, then it fits the criteria to be a member, so it should. It's a logical loop. The statement folds back on itself, creating a contradiction that logic cannot measure or resolve. It is a sentence whose logical length is undefined. A simpler version is the liar's paradox. This statement is false. Try to determine if it's true. If it is true, then it must be false. If it is false, then it must be true. Your brain hits a wall, trying to trace a path that has no end. This revealed a fundamental crack in mathematics, formalized by Kurt Gödel. His incompleteness theorems showed that in any sufficiently complex logical system, there will always be true statements that cannot be proven within that system. These are like points on a map that the map itself tells you exist but can never provide a route to. Our own perception has similar breaking points. Look at a Penrose triangle. You can see it, your brain accepts it, but you know it cannot exist in three-dimensional space. Each individual corner of the triangle makes perfect geometric sense. The connections are locally valid. But when your brain tries to assemble the whole object, the global structure is a contradiction. The information collapses. It's a visual line you can trace with your finger, but you can't build it. The path it describes is shorter than what is required for a real object to exist. Even basic arithmetic has these points of collapse. We are all taught that you cannot divide by zero. But why? Division asks how many of this fit into that. So how many zeros fit into the number 5? An infinite amount. But plotting this on a graph reveals the problem. As you approach zero from the negative side, the answer races towards negative infinity. As you approach from the positive side, it races towards positive infinity. At the exact point of zero, the line breaks. It's a single point of undefined, contradictory, infinite value, a singularity in the number line itself. But what if a line could be more than a line? A space-filling curve, like the Hilbert curve, is a one-dimensional line that can pass through every single point of a two-dimensional square. Think about that.
A line, by definition, has no area. A square obviously does. Yet this infinitely long, infinitely crumpled line manages to touch every point within that area. It has the length of a line, but the coverage of a surface. It fundamentally challenges our concept of dimension itself, proving that a line can be so complex it takes on the properties of a higher dimension. This blurring of dimensions might be fundamental to reality. At the smallest imaginable scale, the Planck length, physicists suspect that space-time is not smooth. It's a chaotic, roiling sea of quantum foam, where particles and antiparticles pop in and out of existence. Down here, the concept of a straight line is meaningless. The shortest distance between 2 points is an impossible path through a constantly changing fractal-like landscape. Any path you could trace would be, for all practical purposes, infinitely long. The very fabric of the universe might be woven from lines that are infinitely longer than the space they seem to occupy. From coastlines to logic, to the fabric of space-time, these paradoxes all tell us one thing: the map is not the territory. Our models of reality, our lines, our equations, our logical statements are just that, models. They are useful simplifications. A line shorter than itself is what happens when our map tries to describe its own edge, or a detail too complex for its scale. It's a sign that we've reached the limits of our current language for describing the world. It is not a failure, but an invitation, a pointer towards a deeper, more complex territory waiting to be explored.